Hello, my name is Tony, and today I will be presenting our work on latent state models for MetaRL. Consider a robot tasked with performing maintenance in a data center. The robot must be able to insert cables of different shape, size, and color into different locations and orientations, operating from onboard sensors such as cameras. In principle, DeepRL can directly map observations to actions and produce a good policy. But in practice, this is highly inefficient and doesn't offer a way to reuse knowledge to learn a new but related skill, such as inserting a new type of cable or inserting in a new location. Typically, these problems are tackled separately. State estimation is used to handle sensory observations, while meta-learning is a promising approach to quickly learn new skills. In this work, we show that by casting meta-RL as an aspect of latent state inference, we can derive an efficient image-based meta-RL algorithm. State estimation can be achieved via unsupervised learning of latent state models, denoted here as inferring state Z from a history of observations X. These approaches summarizes information from high-dimensional inputs into a compact latent representation, and address partial observability by aggregating information over time. Separately, meta-reinforcement learning tackles the problem of quickly inferring task relevant information when faced with a new task. In a graphical model, a hidden task variable tau influences the dynamics as well as the rewards. The unknown task variable is a natural assumption in settings when it is difficult to directly provide precise task information, such as masses or friction properties of objects. Consider a set of tasks involving Ethernet cable insertion. Meta-RL algorithms can be formalized as a function f(phi) that summarizes task-relevant information gleaned from experience into a variable ct, and a policy that conditions on ct to adapt to a new task. During meta-training, both the function f and the policy are trained to maximize the return of the adapted policy across a set of training tasks. After meta-training, the agent adapts to a new task by inferring ct. In our work, we cast latent state estimation and meta-RL into the same framework by melding the state and task hidden variables together into one latent state that is inferred at each time step. We call this approach MELD for meta-RL with latent dynamics. To learn the MELD model, we use a sequential VAE, making use of the same network architecture as in the SLAC algorithm. We maximize the evidence lower bound, which consists of a reconstruction term of observations and rewards, and regularization terms. Note that we reconstruct both observations and rewards to capture state and task information. We use the learned latent belief Q5 as input to the model-free RL algorithm soft actor critic. All losses are optimized with batches of trajectories from training tasks sampled from the replay buffer. At test time, MELD acquires a new skill via posterior inference in the learned model. At each time step, the policy conditioned on the updated belief Q5 to modulate its behavior. We evaluate MELD on several simulated domains using the Mujoko simulator. Similar to existing meta-RL benchmarks, in these environments, we use a shape reward given at each time step. We compare MELD to previous meta-RL algorithms PEARL and RL squared, as well as latent state inference algorithm SLAC, which does not perform meta-learning. Across these domains, we observe that MELD is the only algorithm able to achieve consistent task success, plotted with a dashed black line. In a previous experiment, the task was identifiable given rewards from a few time steps of experience. In more realistic scenarios, the robot might require much longer to figure out the new task. In this environment, the robot receives a reward only when the correct button is pressed, indicated for visualization with a white dot. For analysis, we predict the distance from the robot's end effector to the correct button, given the latent state at each time step, plotted in red. The true distance is plotted in black. In the first episode, the robot explores each button until it finds the correct one. And in the second episode, the robot returns immediately to the correct button. The distance prediction error decreases as more buttons are explored and is very low once the button is found, indicating that the latent state indeed contains task information. Finally, we demonstrate MELD performing Ethernet cable insertion with the WidowX robotic platform. The task distribution consists of the location and orientation of the router, as well as which port to insert. Like the previous experiment, reward is given only when the cable is inserted into the correct port. Here, the robot first explored the left hole, which is incorrect, then finds the correct hole on the second episode. Here, the robot finds the correct hole on the first trial and returns there immediately on the second trial. Thank you for your attention, and we look forward to discussing our work with you at our virtual poster.